Hello friends, welcome to this video. You'll be excited to know that a little damage may arrest further damage in a structure during earthquake. Let us see how it works. So we have taken two elements of the system, say a column element and a beam element. The column element has the stiffness given by 12 EI by L cube, and the beam element has stiffness 4 EI by L for rotation and 6 EI by L square for differential translation of the two ends. Now if we consider a building together, then how to get the stiffness? It is the appropriate summation of all the member stiffnesses taken together. The summation is neither arithmetic summation nor algebraic summation, but it is what is called assembling the stiffness. So we can say in a way that the global stiffness is equal to summation in a particular way of the stiffnesses of all the members in the structure. Now in the stiffness expression, always I is there, the moment of inertia of the section. The moment of inertia of the section is given by b d cube by 12 for a rectangular section, where b is the width of the section and d is the depth of the section. So now if we change the value of b and d, I also will change. If we reduce the value of b, I will change proportionately. If we reduce the value of d, I will change even proportion to the cube of the depth. So changing the size of the beam in either breadth or depth, you actually change the stiffness. Now the time period of a structure is given by T equal to twice by m by k. M is the mass and k is the stiffness. So mass more means time period is more, stiffness more means time period is less, and stiffness less means time period is more. So this formula implies larger the stiffness, smaller is the time period. Smaller the stiffness, larger is the time period, because k is there in the reciprocal of the expression at the bottom. Now this implies when the stiffness is large and the time period is less, it indicates the structure is stiff. It vibrates rapidly. On the other hand, when this stiffness is small and the time period is large, then you can say the structure is sluggish, moving slowly, and the structure is said to be flexible. Stiff structure may exhibit brittle failure even at lower displacement. When it is stiff, it may exhibit like this. Flexible structure can withstand failure even at larger displacement. So a little flexibility in the structure will come to our advantage. Now damage reduces stiffness, we have already understood. Let us see further. We have taken a column here and a beam here. So during earthquake, due to the to and from motion and the inertia effect, some damage has taken place in some part of the column, some damage has taken place in some part of the beam. So as a result, what happens, the sectional size of the column is now lesser. Similarly, sectional size of the beam is now lesser. So that is what we are showing here. The original sectional size of beam or column, say, was b by d. After damage, the top and bottom has got damaged, sides have got damaged. So you have a effective breadth available now. We are writing it by b damaged, which is smaller than the original b. Similarly, the damaged depth is d damaged, which is smaller than the original depth d. So this is what we have written here. These are smaller than the original values. Now I is equal to b d cube by 12. So if b and d have changed and got reduced, then I also has got reduced. So we can say I damaged is less than the original moment of inertia I. And if you remember our formula, T equal to twice by m by k, now say the stiffness also has reduced. So we can write k damaged is less than k, less than the original stiffness. Now we start with this, k damaged is less than k, and our time period formula we have already seen T equal to twice by m by k. So now k here is lesser. So T damaged, the time period of the damaged building is now given by twice by m by k damaged, where k damaged we have seen earlier is lesser than the original value k. So what does it indicate? since this is lesser, reciprocal at the bottom, denominator is lesser, so result will be higher. So T damaged is greater than T. So the time period of a damaged structure is now more than the time period of the original structure. Now we have taken the two spectra, one the Indian spectrum, design spectrum in IS 1893 2016 and EC8 spectrum from Eurocode. So the general nature is, in the beginning it rises and goes to a point and then remains flat for some time, and then it gradually falls parabolically downward. So we shall be concentrating in the present study, present discussion, the domain where it is falling. Time period, with respect to time period, the spectral acceleration ratio SA by G is gradually falling. So we are considering this part of the spectrum for our discussion. Now let us take the spectrum in a schematic way and see what happens, what are the fallouts. We have already seen our damage time period was larger than the original time period here. So along the time period axis, damage time period is here and the original time period is here. So obviously for the original time period, the SA by G ratio was here, SA by G, and for the damaged time period, SA by G ratio is here, which is lower, much lower than the previous one. Now look at the base shear. The base shear standard formula, which is more or less same in other countries also. In Indian code, this is the formula: V base shear, VB equal to Z by 2 I by R SA by G W. For our case, we are considering the building, Z is constant, I is constant, R is constant, because we are considering same building only in the undamaged condition and in the damaged condition. So seismic weight also remains same, W is constant. So what is changing? Only SA by G ratio. Now as we see here, the SA by G ratio for the damaged condition is lower, so SA by G damaged is less than SA by G original. So if you fit in this expression, you get BB damaged is less than the BB original. So the base shear of the damaged building is lower than the base shear of the original building. Damaged structure attracts less base shear. Some damage will try to arrest further damage. So because of the damage, earlier base shear was larger here. Because of some damage, the base shear has got reduced. So now damage will be lesser. So that is what we wanted to highlight, that a little damage may arrest further damage in the structure, because the force attracted in the structure is now lower. And obviously as an outcome, the damage also will be now lower. So we have to make a caution here. The conclusion does not mean that we should deliberately wish damage in our structure. Not like that. It is just a principle or observation. The principle does not hold good for the flat part of the design spectrum. At the top you have a flat part where it will not work. We have seen this works in the falling parabolic part. So what are the time period range for this? It is generally say about time period more than 0.55 second. For all those structures, this will be applicable. For a building, say a 6-story building will be exhibiting this, because it will fall in the falling part, parabolic part of the spectrum. Thank you very much for watching the video. Put your comments in the comment box to encourage, and give your queries in the comment box. I shall try my best to answer your questions. See you again in the next video. Thank you.